Hello and welcome. Now that we understand dynamic memory allocation, we have to implement it. We have to actually know how to do it in C code. So we're going to talk about three really important functions: malloc, calloc, and realloc. And you see that they sort of have names where memory allocation, calloc, and reallocation. The simplest and most common way to allocate memory is through the standard library function named malloc. This is allocating dynamic memory at runtime. In order to call this function, you need to include the standard lib header file. You specify the number of bytes of memory that you want allocated as its argument. What's returned from this function is the address of the first byte of memory that is allocated. Because you get an address returned, a pointer is the only place to put it. Right? So this is why dynamic memory allocation is only possible via this concept of a pointer, because it returns addresses. You can only put an address in a pointer. That's what a pointer stores. A pointer stores an address. So here's how you do it. Very simple syntax. When you create your pointer, when you create your pointer, you don't have to. You could create your pointer and set it to null, and then in the next line you could malloc. But here is the standard syntax. You're creating your int pointer to a type int, and then you'll notice that you call malloc, and in here we're saying malloc, we're gonna create 100 bytes for malloc, and then we're gonna cast it to an int pointer. Because malloc only returns a address, you have to cast it to an int pointer, because that address is storing an int pointer. This is the standard way to do it. Now, you're requesting 100 bytes of memory and assigning it to the address of the memory block to p number. P number is going to point to the first int location at the beginning of the 100 bytes that were allocated. So what this means is, since integers are 4 bytes apiece, it can hold 25 int values. And again, this is assuming that you have 4 bytes. Now, depending on the system that you're running, they may be larger, maybe smaller. So you should see the problem with this. This code's not going to work on different systems because you're allocating based on an assumption, based on the assumption of the int size. So it's not really good to use malloc in this manner with a constant number, 100. What you want to do is you want to use the size of operator. So it would be better to remove the assumption that ints are 4 bytes. Instead, if you want to allocate room for 25 integers, inside the malloc argument, specify the number of integers you want to allocate and then multiply that by the size of the integers. And this will make the code much more portable. This code will now work on different systems, different operating systems, different architectures. You still cast the return value, the address, because it has to be pointing to a type int. So you say int star. The only difference here is you use the size of operator. Size of operator is really important when you're allocating memory using malloc or using calloc or realloc. You always want to use the size of operator for the type that you're allocating, and then multiply that by how many particular numbers you want. So if you want to store 25 ints, you do 25. So the argument of malloc above is clearly indicating that sufficient bytes for accommodating 25 values of type int should be made a variable. Also, as I mentioned, notice the cast. This converts the address returned by the function to the type pointer to int, an int pointer. Malloc returns a pointer of type void. That's what it makes it so useful, right? It returns that address, but it's a void pointer. Remember, we talked about void pointers and why void pointers are useful, because now you can have a function that can take different parameters and it can return a void pointer. Now you're seeing the power of returning a void pointer. But to use it, to actually assign data to it, to dereference it, you have to cast it. Right? If we didn't want to cast this, we could say void star p number. We don't cast it, but then we would have to eventually cast it once we wanted to dereference it. But that's why we have to cast for malloc. It's returning an address and you want it to point to a int type, and it's returning a void type. You can request any number of bytes. However, it is dependent on your system and how much memory you have on your system. So if you try to create or try to request a ton of bytes, or there's some limitation, it could fail. And when it fails, it returns a value of null. Malloc will return null. And this is good because pointers, when pointers are pointing to null, it means that they're not pointing to any memory. So you can't corrupt or change any memory inadvertently. So it's always a good idea after you do a malloc to immediately check for null before you use it. Just like it is when you assign data, or just like it is when you dereference a pointer. You want to make sure that you're actually pointing to something. So here we're allocating some memory for p number, our pointer, and then we're saying if not p number. Remember the null is a 0, so you can just use a not on it. You don't have to actually compare it to null. You can compare it to null. It makes it more readable, maybe makes it more explicit. But you can just say not p number, and that's actually saying not 1, and null is 0. So this will check for null, and if it is null, that basically means that memory was not able to be allocated. If you're not able to allocate memory in your program, you're in trouble. And so what you should usually do in this code to deal with a memory allocation failure is you should abort. You should call exit. You should get out of your program, because if your program can't allocate memory, your program's hosed. So usually you call an exit or an abort if you can't allocate memory. You can also, at least when you do this, you can display a message, terminate the program. It's much better than allowing the program to continue when we're not able to allocate memory. Because then you may continue, you may try to use that memory. It's going to be null, so the program's going to crash anyways, but you're not necessarily going to know why. You'll have to look at the call stack. It will take a lot longer to debug that error. Releasing memory. Now, I mentioned that since the programmer is responsible for allocating the memory, you have to get rid of the memory when you're no longer using it, because memory is a vital resource, especially on embedded systems. You shouldn't be using memory if you don't need it. So you have to release the memory. You always want to release the memory when it's no longer required. Memory that you allocate on the heap will be automatically released when your program exits, which is good because it does do some cleanup. But it's much better to explicitly release the memory when you're done with it, even if it's just before you exit. It's cleaner. Always do it free, or always release the memory after you allocate it. You want to follow this rule. This is a stringent, strict rule. Always release memory if you allocate it. A memory leak occurs when you allocate some memory dynamically and you do not retain the reference, so you're unable to release it. Maybe you're out of scope for that reference. You don't release it. That's called a memory leak. There's memory allocated, but it's no longer being used. This often occurs when you're in a loop and you're allocating memory in a loop. You're in the loop, you allocate this memory, you use it inside the loop, and then you jump out of the loop and you no longer release it. Each loop iteration is allocating it. So to free memory that you have allocated dynamically, you must still have access to that address. So usually you want to free memory when you're done using it, and usually in the method that you allocated it. However, if you are passing that memory to another function, and then it's that function's responsibility, but usually you want to release the memory and the function that you allocate it. To release the memory for a block of dynamically allocated memory whose address you have stored in a pointer, all you have to do is call the free function. This is in the standard lib as well. You just pass in the pointer to the free function. And usually after you pass in that pointer, you want to set it to null, because that's saying that you have no memory allocated for it. The free function has a formal parameter of type void star, so you can pass in any pointer type, and it will work. You don't have to actually cast it or anything like that. As long as p number contains the address that was returned when the memory is allocated, the entire block of memory will be freed for further use. Other programs can use that memory. Your program can now use that memory. Significant when you're on an embedded system. And then, as I mentioned, you always want to set the pointer to null to signify that that pointer is no longer pointing to anything. That memory has been freed. There's another nice function called calloc. This has a couple advantages over malloc. It's very similar to malloc, but what it does is it allocates the memory as a number of elements in a given size. And it also initializes the memory. That's the difference, initialization. I talked about the importance of initialization. That's why you always want to initialize data. You want to initialize data so that you understand that there's data in there that you're expecting. When you uninitialize data, there could be data in there that you don't have any clue about. So always initialize your data with something. And calloc is a little bit better because it does it for you. It takes two arguments, it has two parameters: the number of data items for which space is required, the size of each data item. It's declared in the standard lib header. You call it just like you call malloc. Looks pretty much the same way. In this example, we're creating an integer pointer, and we're allocating 75 integers of size of int. So it takes two parameters. It's a little cleaner because you don't have to actually do a multiplication. In malloc, you had to do 75 times size of int. Here you just say 75. you're creating 75 ints, and the size for each int is 4 bytes, or whatever the system returns from the size of operator. But again, what the significance of this is, it's going to initialize all that data as well. The return value could be null if it's not able to allocate that memory, which in turn you should abort. But it's very similar to using malloc, except the big plus is this initialization. All of the ints are initialized to 0, and that's a really big deal, big advantage. It's also a little bit easier to use with the 2 parameters. Let's talk about another function called realloc. The realloc function enables you to reuse or extend memory that you previously allocated using malloc or calloc. So this is a way to dynamically change how much memory is allocated while you're running. So you could initially create so much memory, and then you realize that that's not enough memory. Well, what you can do there is you can just call realloc, and this will reallocate memory. It expects 2 argument values: a pointer containing an address that was previously returned by a call to malloc. So you have a pointer that has some memory allocated, or calloc, and then the size in bytes of the new memory that you want allocated. So this will allocate the amount of memory you specify by the second argument. That's the second argument. It transfers the contents of the previously allocated memory, referenced by the pointer, so it automatically knows how much memory you had previously allocated because you pass in the pointer. And then it will actually add to that, the newly allocated memory. And it returns a void pointer to the new memory. So you have to recast it when you call realloc, just like the other ones. It returns null if you weren't able to realloc, which again is probably a fatal error and you should abort. The most important feature of this operation is that realloc preserves the contents of the original memory area. You're just extending that memory. It may be fragmented because you may not have been able to do it in sequence, but you still have all that memory that you can assign to now. Data. Let's look at an example. In this example, we're going to use malloc, and then we're going to realloc the memory. And then we're going to free it. So here we're creating a character pointer. We're not initializing it to null. We probably should be. But it's not pointing to, it doesn't have any memory allocated to for what it's pointing to. It has memory allocated to store the pointer, which is just an address, but if you try to go to that address, your program would be host. So what you do is you call malloc. Here we're saying malloc 15. We should be doing, this will create 15 bytes for a character pointer. We cast it because it returns a void pointer. So stir is a pointer now that has memory allocated for what it's pointing to. We then can use stir copy to pass in some data to what it's pointing to, a string, and we print out the string in the address. Well, then we realize that what we allocated, 15 bytes, is not big enough. Right? So then we call realloc, and we pass in the pointer, which is stir, and we want to realloc 25 more bytes. And then that returns a void pointer, so we have to cast it again. Now, we're still going to have in memory JSON. So now we can call stir and concatenate it, and we concatenate to the string com, so now it will be json.com. And then we print it out. And then last but not least, probably the most important thing of this feature, so we don't have, or for this slide, so we don't have a memory leak, is we call free. Always call free when you call malloc. So let's take a look at this example inside code blocks. Okay, here's our code example inside our code blocks editor. And the first thing you should notice is we're including the standard lib header file because that's where our malloc functions and our realloc functions are in, as well as our free function. Also, because we're using some stir functions, concatenation and copy, we're including string.h. Now on line 8, we're going to create our character pointer. It has no memory allocated for it. We should initialize this to null because it's not pointing to anything yet. On line 11, we call malloc. Right? And we should probably say 15 times the size of char in case the size of bytes of char is different. And then we cast it into a character pointer because malloc returns a void. We then copy it. If we tried to copy this and we didn't do anything on line 11, the program would crash because we have no memory allocated for what string points to. We then just print out the string and the address. Now we call realloc. We need to store more data than 15 bytes, so we're going to realloc with 25 bytes. And we probably want to do, again, size of char to be consistent. We cast this, and then we concatenate onto our existing memory location that contains JSON, com, and we're going to print out json.com. And then last but not least, on line 20, we free that memory up, which is really important. So let's go ahead and run this, and what you'll just see is that when we print it out the second time, we have the concatenation. So our first string, we have memory allocated, and it's an address 000C29.118. Then we created a new address by reallocating and taking the existing size of the pointer that we passed to it as an argument. So 000C0CD8 actually has more data allocated to it. The existing data in JSON and 25 more bytes. And so what you notice is the concatenation works. Because when we reallocated, we put the contents JSON in that memory, and we just extended it. So a lot of advantages to using these malloc and these calloc and free and realloc calls. You want to use these, you want to understand these. Pretty simple functions to use. So in our last slide, let's just go over some guidelines. You want to avoid allocating lots of small amounts of memory. It's not efficient. When you allocate memory on the heap, it does have some overhead with it. And if you allocate small blocks of memory, it's going to have much more overhead than allocating fewer larger blocks. So allocate the memory that you need, but don't do it every 2 statements, with reallocation. Do large chunks. Only hang on to the memory as long as you need it. Memory is a scarce resource. When it's on the heap, it's even more scarce. So when you're finished with a block of memory, call free. Always ensure that you provide for releasing memory that you've allocated. Decide where in your code you will release the memory when you write the code that allocates it. Make sure you have access to that pointer. If you need to make the pointer global, then you need to do that. But usually wherever you allocate it in that function, you should release it in that function. If you have other functions releasing memory for you, you're then assuming that function, it's just not good because there's too much coupling and dependencies there. The person that creates it should be the person that deletes it. Don't put the responsibility onto other functions and such. Make sure you do not inadvertently overwrite the address of memory you've allocated on the heap before you have released it. This will cause a memory leak. So if you try to write too many bytes to it, or if you have overflows, you may have issues. So be especially careful when you're allocating memory within a loop, okay? Because this can cause problems and buffer overflows. I hope this was helpful. Dynamic memory allocation, a big deal. I'll give you a challenge that helps you become more familiar with this, but make sure you understand this concept. Thank you.